Welcome to another day on the Journey Chez Chem. Please do warm-up questions as we do every day, and I'll see you soon. Now the question in number 1 asked for us to answer how many significant digits are in each one of these numbers. In A, all 3 of these digits are significant because 3 is a regular digit, what I call a regular digit, 1 through 9, and it precedes the decimal, so that is 3 significant digits. In B, these zeros are showing me how small this number is, so the 6, 8, and the 0 are significant. The final 0 is significant because this measurement was made to this accuracy. In C, only the 4 is significant, so only one of those digits is significant. These are all trailing zeros. In D, both of these numbers are significant. In E, all 3 of these numbers are significant because when we have a regular digit in front of the decimal, then they are all significant, which is why in F, all 4 of these digits are significant. In G, again, we have placeholders, so only the 8 and the 0 are significant. Same thing with H, only the 1 and the 0 are significant. Now, it happens to be a 0 because it's exact, but it could have been a 1, 2, 3, 4, 5, 6, 7, 8, 9. So both of these digits are significant. In I, these are trailing zeros, and there is no decimal here, so there are 4 significant digits. In J, these last 4 are significant because these zeros are showing us how small this number is, and it doesn't matter if I have 2, 3, or however many zeros in front of that decimal place, we're not going to fall for that trick, so we know there's 4 significant digits in this number. Now in number 2, you were asked to change these numbers to scientific notation. So because this is already one whole number in front of the decimal, it's the same number, but it's 10 to the 0. 10 to the 0 is equal to 1. So because I have to put it in scientific notation, I still have to show times 10 to some value. In B, this number is less than 1, so I have to move the decimal behind the first regular digit, so that will be 6.80 times 10 to the minus 3, and I have to show this 0 because it was significant. In C, it's only 4 times 10 to the 4th. In D, it's 1.0 times 10 to the 0 again because it's already one whole number in front of the decimal. In E, I do have to move that decimal one place, 2.5 times 10 to the 1. Oh, no. It should be 2.50 times 10 to the 1 because the 0 was significant. Therefore, when I change it to another number, I must show that 0 that was significant. Very, very important point. I'm glad I made that mistake so you could see how I could fix it. In F, 1.500 times 10 to the 1. Again, if I have 4 significant digits, I have to have 4 significant digits in my converted number. And sometimes scientific notation is the only way that we can get the right number of significant digits that we need in our answer. And G, we have 8.0 times 10 to the minus 4. And H, we have 1.0 times 10 to the minus 2. And I, this number is larger than 1, so I have a positive exponent, and I'm going to move it 3, 6, 8 places. So it's 3.204 times 10 to the 8th. In the last one, this number is less than 1, so it has a negative exponent, and I'm moving it 3, 6 places So it's 2.780 times 10 to the negative 6th would be the answer to number 2J. Now I need to speak to you a little bit about conversion factors. They're very, very important. So when we do conversion factors, and I always want to see that conversion factor, we're not going to use that King Henry moving the decimal thing because we can make lots of mistakes that way. Sometimes we get it right, sometimes we get it wrong, but with a conversion factor, you never get it wrong. So I'm going to show you how we use conversion factors, and they're also called factor label method. Oh, but to love those conversion factors. Well, what is a conversion factor? A conversion factor is a fraction whose values equals 1. So it's a fraction where the top and the bottom number, the values are the same, so overall it equals 1. Now it's important that you write these things down because they'll help you when you first start doing conversion factors. When we have a fraction, in the numbers in the top we multiply, and the numbers in the bottom we divide. If we have exponential numbers, we add the exponents if we're multiplying, and we subtract the exponents when we're dividing. So these are to help you know which way you're going. Now I'm going to start with a very straightforward one, and we'll work towards a little bit more difficulty. If I know that there's 1,000 milliliters equals 1 liter. Therefore, if 1,000 milliliters is equal to 1 liter, I could also say that 1 liter is equal to 1,000 milliliters. It just depends where I'm going. And so when I have a conversion factor on the top, I want to put what I want, what I'm looking for, and in the bottom, I put what I want to cancel or what I want to get rid of. So, if I have 16 liters and I want to go to milliliters, liters has to be in the bottom so that the liters will cancel. And I get what I'm looking for, which is milliliters. Every number that I start with, I should always put over 1, because any number over 1 is the same number. And then I have to figure out how many of one to the other. Well, there are 1,000 milliliters in 1 liter. If I change this to an exponent, this would be 1.6 times 10 to the 1, and this is 1 times 10 to the 3. So when I'm doing exponents, I add them when I'm multiplying. So the top numbers I'm multiplying, so 1 plus 3 is 4, and my answer is 1.6 times 10 to the 4th milliliters. If I'm going in the opposite direction, and I have 1,300 milliliters, and I want to go to liters, then I use the conversion factor in the other direction, where 1 liter is 1,000 milliliters. Well, this number is 1.3 times 10 to the 3, and this number is 1 times 10 to the 3rd, and so 3 minus 3 is 0, and my answer is 1.3 liters. Now, I don't have to put it in scientific notation. I could, that's perfectly correct, but I don't need to do that. So this is called a one-stepper. We just have to do one step. Well, sometimes we have to go to our base unit first because we don't want to memorize all of those conversions on the top of the page of worksheet B. We want to be able to learn the basics and go from there. So what I can do, if I have 345 nanometers and I want to go to kilometers, first I have to go to my base unit. And my base unit is meters. And what I want to cancel has to go in the bottom, nanometers. And I'm going then to kilometers. And what I need to cancel here is my base unit. So then, once I get my units in order, then I just have to go back and say how many of one to the other. Now I know that 1 meter is 1 billion nanometers. And we know that 1 nanometer is equal to 1 times 10 to the minus 9th meters. But I don't like to use negative exponents, so I try to say that there are 1 billion nanometers in 1 meter, so that I keep a positive exponent. It doesn't matter, you can do it either way. I just prefer to use positive exponents because we like to have a positive attitude as well. So then I go to the next step, and 1 kilometer is 1,000 meters. So I have exponents here, and this number is 3.45 times 10 to the 2. So 2 minus 9 is minus 7, minus 3 is minus 10. So my answer is 3.45 times 10 to the minus 7th kilometers. So that's how you do that type of problem. Well, if I was going in the reverse direction, I might just have to flip these over. The most important thing to remember is that my units have to cancel. Because if I had meters here and then meters here, that'd give me meters squared, and that wouldn't be very much help at all, would it? So we need to make sure that our units cancel and that the number in the top and the number in the bottom are equal to one another. And then that should work out perfectly well. We don't have to worry about moving the decimal, it'll just move itself. So you try that worksheet, and your facilitator will go over it with you, and tomorrow's warm-up will be lots of conversions so we can try it again. So I will see you tomorrow.